the concept of wave function. So one of the important topic from quantum mechanics. So everything begins with the concept of wave function. So before going to start, if you are new to my channel, please subscribe my channel for upcoming videos. Let us discuss. So wave function is used to find the particle position. As we have in classical mechanics, particle behaves like particle and wave behave like wave. But in quantum mechanics, wave behave like particle and particle behave like wave. That is according to de Broglie wave. We call them as matter waves. So whatever the wave, if you take every quantity is always associated with any kind of wave which varies periodically with space and time. So as I said, this was explained by de Broglie, and that's why we call de Broglie waves or matter waves associated with moving particle. The quantity that vary with space and time, we call that as wave function of the particle. So wave function we can define as the quantity that vary with space and time. The temporal means dependent on time, and spatial means dependent on position. So the temporal and spatial evolution of quantum mechanical particle is described by the symbol. We have the wave function, that is psi x comma t. X comma t stands for one dimensional. If we take r comma t, that is x y z, r represents all the three coordinates. So this is for three-dimensional motion of the particle. So it contains all possible information of the state of the system. Wave function gives all the information about the state of the system. So what are the conditions for a physically accepted, well-behaved, realistic wave mechanics? So first condition is the wave function psi of r comma t should be finite. It must have finite value and finite and single value and continuous everywhere in space. So this is the very important and first condition, that is wave function must be finite, single valued and continuous everywhere in space, and the differential form of wave function should be continuous everywhere in space, but the differential form may be discontinuous in same cases. So this condition you should remember. So differential form may or may not be continuous. It depends upon the situation. So the third one, if the potential under which the particle is moving has an infinite amount of discontinuity at same points. So if we consider the potential energy of the particle which is moving has a infinite amount of discontinuity at same points. So this when wave function is discontinuous, if the potential under which the particle is moving has infinite amount. Okay. So as we have the first condition, wave function is finite. So that's why if the potential under which the particle is moving, if it is having the infinite amount, then that is going to be discontinuous. Wave function psi of x comma t should be square integrand. If we take the probability of finding the particle, we will take the mod of the square of wave function. So that's why we represent like this. Integral from plus to minus infinity is equal to which is a finite quantity. always we represent the square of the integrand. So let us take some examples. First one, which of the following wave function is acceptable as the solution of the Schrodinger equation for all values of x? So Schrodinger equation is for total energy, nothing but Hamiltonian, is equal to kinetic energy plus potential energy. So here they have given the four option. We have to find out which of the following wave function is acceptable. So if we read these conditions, we can solve this. So if we take the four conditions here, wave function is equal to a sec x tan x, and 2 are in terms of exponential. Let us solve this. So the first one, if you take the wave function is equal to a sec x and psi of x a tan x. If we put the value of x pi by 2, that means they are going to be infinite. As we have, if we put the according to trigonometry, sec pi by 2, tan pi by 2, they are not infinite. And if we take these exponential, if we take the value of x is equal to plus or minus infinity, they are also, this is a third option is also not finite. First one is also not finite and tan is also not finite. That means they are infinite. If we take the fourth option, if we put x equal to plus or minus infinity, which is finite everywhere in space. So here the correct option is fourth one, which is the finite everywhere. That's why this is the acceptable wave function for Schrodinger equation. So next example, a ball bounces back of Earth. You are asked to solve this quantum mechanically, assuming Earth is an infinitely hard sphere. Consider surface of Earth as origin, implying a potential is equal to 0 when x equal to 0, and a potential elsewhere, that is v of x is equal to minus mgx. Whatever the gravitational energy, if we consider, the potential energy must be minus mgx. Which of the following wave, because it is bouncing back to the earth, is physically possible for this problem? Here is the condition, k must be greater than 0. Here four options have been given. So let us solve this one. Since the earth has been taken as infinitely hard sphere, therefore the wave function of ball will be 0 for the x less than 0 and non-zero for x greater than 0 and 0 at infinity. Wave function of the ball will be 0 for x less than 0, and wave function is non-zero for x greater than 0, and it is 0 at infinity. Then wave function psi of x should be continuous everywhere. The wave function of the ball will be 0 at x equal to 0. So we have three conditions, x less than 0, x greater than 0 and x equal to 0, which is infinite. And here the according to the wave function condition, what we have, wave function should be continuous everywhere and the wave function of the ball will be 0 at x equal to 0. So correct option is option D here also. a into x e to the power minus kx square. Physical significance of wave function. Generally, wave function is a complex quantity. It can be multiplied by any complex number without affecting its physical significance. So, in general, the wave function has no direct physical significance but quantity. As I said, the usually we denote the square of the mod of wave function. Psi of x comma t mod of square is a real physical quantity which has physical significance and is defined as the position probability density, probability of finding the particle per unit length at time t. Therefore, for one dimension, the probability of finding the particle between x to x plus dx at time t is given by, we have to take the wave function and its conjugate psi star. Then we will have the mod of square of the wave function, which we call probability of finding the particle. So, for 3-dimensional, we have to take here r comma t. For 1 dimension x comma t. So, for 3 dimension r comma t, that is what the square of the mod of psi of r comma t for 3-dimensional. Deta is volume. Finding the particle within the volume element deta. So, we should also understand here normalization and orthogonality condition. The wave function psi of x comma t or r comma t should be chosen such that total probability of finding the particle in the entire space should be equal to unity. That means the mod of the square of wave function should be equal to 1. That is for 1 dimension, and for 3 dimension psi of r comma t square within the volume element should be equal to 1. This is what we call normalization condition of wave function. So let us discuss here the normalization condition. So method of normalization. Consider here another wave function phi of x comma t is unnormalized wave function. We can construct a normalized wave function as psi of x comma t is equal to n into phi of x comma t, where n is normalized constant. Therefore, so according to the normalization condition, we should write the equation here. Psi star into psi in 1 dimension is equal to 1. So then n we can take here because conjugate, if you take n into n square. So n is equal to what? 1 divided by under root integral of phi star into phi, which is unnormalized wave function. So we can have the equation for normalization, that is capital N is equal to 1 of under root phi star into phi. So let us solve one example here. Normalize the wave function given by, so the wave function they have given as two condition, x is greater than 0 and x less than 0, that is equal to n e to the power minus alpha x n e to the power plus alpha x. So let us substitute here. The normalization condition is what? Integral of minus infinity to plus infinity psi star into psi. Psi value you have to substitute here. Once you substitute, take the limits here minus infinity to 0 and split that. Minus infinity to 0, 0 to plus infinity. Then we can write it as exponential e to the power alpha x e to the power minus 2 alpha x. equal to 1, because x greater than 0 and x less than 0 they have given the limit. So according to that we can write in terms of exponential. So n square is common, you can take. Once you integrate with respect to dx, we will get 1 divided by 2 alpha for both, that is equal to 1. So n will be root, if you take n is equal to root of alpha. This is what the normalization condition for the given wave function, n is equal to root alpha. Similarly, we have the orthogonality condition of wave function. That means the two wave functions im, let us take im of x, in of x are said to be orthogonal if the integrand minus infinity to plus infinity m star into n dx is equal to 0. Integrand must be equal to 0. That means it is obeying orthogonality condition. And one more thing, m should not be equal to n. If a particle is in the state m of x, then particle cannot be in the state of n of x simultaneously. That's why m should not be equal to n. So orthogonality condition of the wave function, once we understand, so next we can also discuss the Hilbert space. In a vector space, the set of unit vectors, nothing but 1, en, e1 cap, e2, so on, form the orthonormal basis. That is, we can express an vector in this vector space as a linear combination of all the unit vectors. Similarly, a space can be defined in which set of function phi 1, phi 2 and phi 3 of x form the orthonormal basis of the coordinate system. The corresponding infinitesimal linear vector space is called Hilbert space. So first we should consider the set of unit vectors which form the orthonormal basis. Orthogonality condition is 0 and normalization condition is 1, as we have discussed here above orthogonality and normalization conditions. So the set of unit vectors from the orthonormal basis. So then we can express the vector space as the linear combination of the unit vectors. Similarly, a space can be defined in terms of wave function. Linear combination of wave function phi 1, phi 2, phi 3, which also should form the orthonormal basis. That means orthogonality and normalization condition, they must obey basis of the coordinate system. So such type of infinitesimal linear vector space is called Hilbert space. Hilbert space, if we take, that is what the linear vector space, infinitesimal. Whether it may be in terms of unit vector, set of unit vectors, or in terms of set of wave functions, if we take that, they must form the orthonormal basis. Then we call that as Hilbert space. So what are the properties? Let us discuss. First one, the inner product or the scalar product of two function psi of x, psi j of x defined in the interval, that is between x between greater than or equal or less than or equal to b, which we can define it as the expectation value we call. I will discuss about expectation value in the next class. Psi I, psi j is equal to a to b psi I star psi j of x. So this is what the inner product or scalar product of two functions, if we take between the given interval, we can write it as the integrand of psi I star and psi j star, conjugate of these two wave functions, inner product. So second condition, two functions psi I and psi j are said to be orthogonal if their inner product is 0. So we already discussed the orthogonality condition, that is equal to 0. So the inner product of these two wave functions, if we take, they must be orthogonal. And second condition, so another condition, so this is what orthogonality condition, and that is psi I psi j is equal to integrand of psi I star psi j star is equal to 0. So normalization function, if we take, the norm of the function psi of x is defined as n is equal to root of expectation value of psi I is equal to integrand of psi I star conjugate of that wave function, that is root of the integrand of psi star psi, normalization of the wave function for Hilbert space. And a function is said to be normalized if the norm of the function is unity. So first, this is n is equal to norm of the function, and normalization condition is what, equal to 1. So these are the properties of Hilbert space. So first condition is the inner product is what, integrand of psi star into psi, and the two functions inner product must be 0, that is what, orthogonality condition. And the norm of the function is given by the equation n is equal to root of expectation value of psi I, and the function is said to be normalized if its value is equal to 1. So this is all about the significance of wave function, and with some of the examples. I hope this is helpful for you to understand the concept of wave function. So one of the topic from quantum mechanics. So in the next video, I am going to discuss further about the topics of quantum mechanics. Thank you for watching.